Hi, congratulations on coming so far in the calculus journey here. You're up to the last application of the derivative. It's called optimisation. And I guess you can see from that word, optimum means best solution. And so we want the optimum or best solution here. And as you can see, possibly that's a minimum, lowest cost perhaps, or a maximum profit perhaps, using an economic sort of model here. And where does that come into the calculus? We'll come over here. Of course, the max or min can be found, the local max and local min can be found using derivative equal to naught. So that's where it all fits in, and this is an exciting application because we're doing something practical with our calculus. And the important thing to realise, though, in a practical problem, we will be able to say how far to left and right here we can go with x's, or the domain. So you can see in this graph here, if we're allowed to go out as high as x equals b, you actually do get a y value which beats this local effect. In this particular example, we've gone out to x equals a, and that isn't lower than our minimum there. But we've got to check the end conditions there, what are called end conditions, global conditions if you like, how far in practice you can go along the x-axis, keeping in mind that you may beat the local effects there. So it's an interesting section of the work, and I've got up here the first problem we're going to do, where we're looking at perhaps putting walls in to a shed and dividing it up. And what's the cheapest way we can do that? What's the minimum cost? What's the optimal solution? So let's come down and have a bit of a summary here, and I've used Hayes and Harris again here, so it would be good to have a copy of that to track through. And they're saying here in these problems that I mentioned to you, we're finding the maximum or minimum value of a variable so that we can find maximum or minimum cost or surface area or something, and have an optimum or best situation. So that's a pretty good description there. Now I guess already in your own mind you would be aware of some of the steps, and Hayes and Harris here have formalised it, saying, well, it would be good to start off with a diagram. And if it is a problem that you can summarise with a diagram, this is very good. And also here, place on the diagram all given info. That's important, because in this course you will need all the information we give you. We don't give you any extraneous information. So if information is given, it's important to put it there and to remember to use it at the appropriate stage in the problem. So you know now also that to find the maximum or minimum value of a function, you have to have a function, don't you? So we have to have a formula or an equation with a variable in it, and trying to find the maximum or minimum value. You know why? Because if it was a maximum or something, you have to put it on the calculator in y and x land. I mean, usually we'll be working in things like surface area and lengths, A's and L's. It's important to stay in context. But when you go to technology, it's y and x land. So here we know you can't have, with technology, more than one variable. Otherwise you can't easily graph it on the calculator. So we do need one variable. So something like v equals a third pi r squared h for volume of a cone. You would try to get rid of the h in there so that you would just have r's in it, get h in terms of r. And somewhere in the given information they will give you a clue as to how to do that. And of course you do need a single variable in a calculus approach. So this is technology, but if you use the calculus, you want to put the derivative equal to naught. You again don't want two variables in there. You want just a y and x type situation. So here you might have v and h might be twice the radius or something. So you get it all in r land. So you can then dv by dr it. Do you get the idea of a single variable? So these steps are quite clear because you know where you're headed. you know that you're going to try and find the derivative for that local max or min and put equal to naught, because here that's our next step. And then you're going to check out whether it's a max or a min. And so all these steps are pretty well known to you. We're just formalising there. Okay, so if you do have 2 points at which the derivative is naught, you know your next step is a sign diagram, and here it will generally be, let's say R, and this is the sign diagram for dv by dr. Must contextualise it in this application now, and you might have positive, negative, positive, do it this way, and you have a local max or a local min, these local effects, local max. This is what we always must do. We cannot assume it's a max or a min. Okay, you could check it with the calculator, but generally we have to do it with calculus. So it's a full mathematical treatment. Okay, so that's one way of finding out whether it's a local max or min. The other way is with the second derivative. So if we stay in V and R's, then we know the second derivative is what? At a local maximum, it's less than naught. The second derivative at a local minimum is greater than naught. So you could use the second derivative test if the second derivative is relatively easy to obtain. And then, of course, it's back to this example again. We have to check the ends. How far to the left are we able to go on the domain or the set of values of the variable? How far to the right? Usually a constraint down here is that x cannot be less than naught, because in practice it's usually a length or something like that. So you check by subbing into the function the two values on the ends, the smallest possible value of the variable and the largest possible value, and see if those end conditions give rise to a function value that beats the local effect. All right, might just pause presentation, go back and think about that, because they are our tools now, and we want to go on and do a problem. So come down and let's have a look at the first one here from Hayes and Harris. So we've got an industrial shed of 600 square metres. Not a bad idea to underline information, so use it all. It's going to be divided into 3 rectangular rooms of equal size, and it's $60 per metre. So there's our information. Here's our diagram, so we've labelled it clearly with all the equal pieces here. And I would also put next to it, area is 600 square metres. So I don't forget that that is something that I will need to use. Okay, in this course, please keep in mind, we don't give you any extraneous information. So if that information is given, you will need to use it. So here's the problem down here. What dimensions should your shed have to minimise the cost of the walls? Minimise, I didn't underline that. Okay, so we have to introduce some variables. So we don't know the relationship in the rectangle. No one says the length is twice the breadth or anything like that. So we have x's and y's in there. Okay, let's journey on towards the cost. So to get the cost, we need the total length of walls. So there'll be 6 x's, do you agree? And 4 y lengths. Okay. Now, what Hayes and Harris do here, I will do later on, because I would say here we're after a formula not for the length. Ultimately, we want the cost. So what would the cost formula be? It would be 60 times 6x plus 4y. I think logically that's where you go next, because we're trying to minimise cost. So let's get a formula for cost. And now our next step is to eliminate one of the variables. I like x's, you've been brought up on x's as well, so let's stay with x's and let's try and get rid of y. And so now we go to the given information. Okay, just keep in mind why this is a $60 per metre, and this is our total number of metres. So given information says, or what haven't we used? 600 square metres written next to the diagram, and then we have, what's the area? 3x by y. Let's just come up and make sure you agree with that. So here it is here. We've got 3 x's as our length, and our width is y. Okay, so therefore we've got this expression down here, and therefore 200 over x equals y. So we're doing fine. Just we make a note that these are positive values, of course, because they mean lengths. So now we can construct our formula. I'm coming in at this stage. Hayes and Harris still working on it there. So 60, leave the x in there, and instead of 4y, we've got 4 lots of 200 over x. So do it like that. They've done it in a slightly different order. Okay, so you've got the function. You could put it straight on the calculator and sneak a peek, but let's have a look at doing it purely with calculus. We say it's a minimum when the derivative is equal to naught. Should make that statement, and then here we have our function. Write it in with x to the neg 1 ready for getting the derivative. Okay, differentiating that, and then we would put that derivative equal to naught. They have not shown that step as such. Putting that equal to naught, transposing the 360, put on the other side, and then rearranging to get x squared as that, and then we have our value of x squared, and taking the square root, should really put in there x is greater than naught, because with a quadratic function there are two solutions, and we're only choosing to use a positive because that's our restriction in our problem. That's a contextual restriction here. So then we need, if that's the length, then what is the y? So subbing it into y is 200 over x. So we've got the dimensions of our shed, and we can work that out. And then we need the minimum cost. So we're going to put 11.547 back in the cost equation, back up there, and find that minimum cost. Please notice that we're working with 3 decimal places, because at the end of the day in money problems, money must be implies to the nearest cent, which is 2 decimal places, so we should work with 3 so that we can round accurately. No one likes to lose even a cent in money. So what have we got now for our floor design? We've got this. Now, you have a technology graph up there that shows that this is a minimum, but we should check this with either the second derivative or with a sign diagram. We really have not got a complete solution until you check that at 11.547 we have a sign diagram for c dash x, that we do have a minimum. So you should put that sign diagram and sub in to the left and right. And if you do that, you'll have a negative and then a positive. That's the easiest way here of validating that it's a local minimum here. What's the other way? Well, you could get the second derivative. How hard is that? Let's go back up here. First derivative is 360 take 48,000 x to the neg 2. So what is it? 360 take 48,000 x to the neg 2. Let's check that again. 360, yep, okay. And so that's the first derivative, and then the second derivative would be, now what is it? It's going to be positive 96,000 x to the neg 3, which is 96,000 over x cubed. And if I subbed in a positive, yes, it would be greater than naught, therefore a local minimum. So you can do either of these methods to classify the turning point, whether it's a max or a min. Okay. So here they have a warning, and back on that same graph again, we've found these points here, and but we should check if we're allowed to go far enough on either end, do they beat that local effect? So here, what would that be? Well, would be 0, would be our smallest value for x, and our biggest value, well, would be when y is, let's go back up here now, here, yeah, if smallest value of x would be 0, the maximum value of x would be when y is very, very small. So what would that be? And if you go up and look at our problem here with our total distances and so on, you can see that it's governed by the area being 600 square metres. We need to go back up here a little bit further again, and saying that here these are our values. So 3x by y is 600. If y is very, very small, x would approach 200. Okay, so we could say there that's our biggest value, and if we then put that into our function, our cost function, we would find here that it does not beat that local minimum. It actually is going to keep going up. So you can't go further than about 200 this way, and so it's just growing. So that would be our check. Notice they haven't actually done that check here. They've used technology to say we can see that is the actual minimum. We should do that check. All right, so let's have a look at what we've done just now, testing optimal solutions, finding where the derivative is naught. Do we know whether it's a maximum or minimum? We should check that with a sign diagram or with the second derivative. Just remembering, if the second derivative from that last application is less than naught, we have a local maximum. Sort of reverse association. Second derivative less than naught, that's a negative. You usually think of that as being small. No, it's the reverse of that. It's actually happening when it's a local maximum. Just a way of trying to remember. A second derivative positive is actually a local minimum. So, and then there's a graph test, of course, if you're able to get a picture of the graph, and technology can help you. But you have to actually substantiate mathematically what you're doing here, rather than, or unless they say you can use technology, rather than just saying, I saw it on the graph, I saw it on the calculator. So that generally won't do. All right, so let's move on now, and let's look at another example. So we're making a cake dish by taking squares out of the corners. Here they are, nice diagram they've got for us here, out of the rectangle, which is 25 centimetres by 40 centimetres. So this is 40 centimetres and this is 25 centimetres, and we're taking out squares. So what size squares should you cut out to have a maximum volume container? Do you see the problem? You could cut out big squares and have a taller, skinnier one or a flatter one. So that's the idea. You will change the shape depending upon how deep you cut these things out. There's all sorts of shapes there. Depending upon, we're going to let that variable be x. X turns out to be the depth, doesn't it, if you cut out x by x there. So let's come down and look at this problem then. So here it is. We're cutting out x by x. So this length has become 25 take 2x. This length's become 40 take 2x. So now the volume, length by width by depth, always good to start off with a basic mathematical formula. Then we substitute in the length, the breadth and the depth, and then we can simplify it, and then we're saying that x is greater than naught, and also 25 take 2x. The two lengths there must both be greater than naught. What is the shorter one? 25 take 2x. So x has to be less than 12.5. We haven't bothered with the 40 take 2x because 25 take 2x is the smallest one. It's going to therefore mean that you can't go over 12.5, otherwise you'll have no breadth of the thing or width of the thing. Okay, so we've got our end conditions here, putting in the constraints on x in practical land. So now we need to get the derivative. So just coming here now, just keeping in mind the product rule, those two things times. So it's the derivative of the first by the second unchanged plus the first unchanged by the derivative of the second. So applying all that out, we've got a quadratic, and then we can factorise it, putting it equal to naught. You'll have this one equals naught, or x is 5 is naught, and then let's have a look at the picture then. So 16 2/3 is too far out. We've said we can't get it out that far. If x is that big, the breadth, which is 25 take 2x, is less than 0, so that is outside our possible set of values. Just coming up here again, noticing we said that. And so now, with the sign diagram, we sub in a value into the derivative of, let's say, 1 from that region. We find it's positive. Sub in a value, let's say 6 from this region, it's negative. Or do you want to do it more mathematically? This is a concave up parabola, which always goes like that. So the sign pattern is going to be positive, negative, positive. And so you can do that. And this is the first section of it, up to 5. And so there, it's first 5, and this is the other one that's out of it, that's 16 2/3. So either way, we have this diagram, and we can see, therefore, it is a local max at that point. Now, the second derivative test, let's get the second derivative, here it is. Put equal to 0, put x equals 5 in it, and we get a negative, and that's less than 0, and so we have a local maximum from both tests. You don't have to do both tests. So the maximum volume is obtained when x is 5, and we cut 5 centimetre squares out of the corners. What have you noticed? What we should do, we haven't checked the ends really. We're saying here, with this volume, this length up here, if x tended to 0, got very small, the volume would tend to 0. Right, and so that's not going to be our maximum. If x tended to 12.5, the volume would also tend to 0, these two ends. Because if x is 0, it's a very flat dish. A volume is tending to 0, isn't it? A very flat dish. And if it turns to 12.5, it's a very broad dish, but it hasn't got much. So it's not a very broad dish, it's tall and skinny. I'm trying to draw a picture here of this one. So it's actually very tall and skinny. So in either case, the volume is going to tend to 0. So that's checking our end conditions, checking that when we go to the smallest and largest x, we don't beat our local maximum. All right, so let's go down and do another one. So here's one here. Infinitely many rectangles can be inscribed in a semicircle. So there's all different shapes of rectangles, aren't there? Put another one in here. Okay. Find the shape of the largest rectangle which can be inscribed. So drawing one rectangle, we've got all our information on there. Now we want to introduce a variable. So here, not a bad one, is the half of the length. You could use the whole length is x, but half the length, that tends to be handy here. X is just that distance. And then what we're going to try and do is the largest rectangle, we're interpreting that means the maximum area. So the maximum area is length by width. So we have to go and say, well, the length is 2x, the width we have to use Pythagoras in here. And so we can say the total diameter is 20, so this is 10 there, and then using Pythagoras. Alright, so I generally would get you to go here first, the area, and then go back from the given information and find y, the width in terms of x as well. The length is already in terms of x there. So here they've got also looking at the restrictions. X must be greater than 0 and x must be less than 10, because two lots of x have to come to 20. They're letting x just be in here. So here x is that much and 2x is the whole thing, and it's got to fit in 20 because that's the diameter. So x must be between 0 and 10. Okay, so next step, just you don't have to put those steps down here as such, but you write this down, then the derivative, and that's using the product rule again, so watch it. Derivative of the first second unchanged plus first unchanged derivative of the second. Don't forget the chain rule there. And so you get some reasonably complicated looking expressions, simplifying it down here in each step here, putting over a common denominator, cross multiplying if you must, and then going on and getting our quotient expression, our simplest one. We don't have to worry about the bottom line because the quotient is 0. This derivative is going to be 0 when the top line is 0. So we only have to put that equal to 0. And if you're able to factorise it like that, there we are. Difference of two squares here. Root 50 squared. Let's get rid of that there. Root 50 squared, take x squared. It's root 50 plus x. Root 50 take x, if you want. Or you could have just put 50 take x squared equals 0. 50 equals x squared. Plus or minus root 50 equals x. Making the proviso down here that x is a positive, so there's only one particular solution that works here in this practical problem, and that's that one there. The root of 57.071. Coming down a sign test for the derivative now, putting it between 0 and 10. We're just reminding ourselves x can't be less than 0 or greater than 10 from the previous discussion. So if you sub in a value of x from here or from here into the function, then you will get these signs. So you can say what the picture is looking like there, have a local maximum, your conclusion here, and then you might, they haven't done the second derivative test here, they made the comment that this is hard to find, very big expression we had, so generally would avoid that method then. They've subbed in 5 and 8 and just explaining these values. Okay, so what's our answer? Then our answer is given on this diagram here, that we've got 14.14 and 7.07 there to, well, they've mixed it, haven't they? This is 3 significant figures, and this is to 2 decimal places, so really probably should be 14.1, keeping it both to 3 significant figures. All right, let's do another one, and then I'll let you loose on some problems, or you might have a good idea now and just move on. So find the most economical shape here. Let's just go back over here and up here a bit. Let's try to locate this one, and let's have a look at the most economical shape, and that's the minimum surface area here for a box with square base. So square base, given that it contains 4 litres, so keep that 4 litres in mind. So what we're going to say is it's square, so it's x by x and then y. So the volume is, here we go, we want minimum surface area. So I would generally go down here first. What's the area? It's that plus that. I'd look at my formula and say, hey, I want to get rid of that other variable. Then I would go and use the 4 litres, and this would come next in my view. I think you should go for the formula, and that's what their steps were earlier, and then when you see that you have a y in there, go back and use that 4,000 cubic centimetres of 4 litres in a length width depth situation to find y in terms of x. Okay, so, and that's coming from there, and that's where we're putting it in. So that idea, get a formula, look at it, go to the given information, remove other variable, remove or replace the other one from the given information. So that's always going to be a pattern. I think you should do it in that order, so that follows a better sort of procedure. So here we have the area. We will get the derivative. We put equal to 0, so that means that we get that equation there, rearranging it then. We've got this, cube root, okay, all on the calculator. Sign diagram, x is 20, up there. How far can you go here? Well, x has got to be greater than 0. because it's a length. And how big do you think you could make x? How would you work that out? I don't think they do that down here. I don't think they check the ends here. Let's have a look. No, they don't. So here we might just go back and check what. We'll just go back up this way here. Let's persevere here with me for a minute. We're just sliding around the place. So let's just go back and check what we can do for the maximum x here. So up here now, here we have it, don't we? 4,000 over x squared equals y. So here, well, let's go for something like y is 1. X squared, let's say, could be approximately 4,000, and y is 1. That's an extreme situation. We could have x actually, or y tending to 0, so that x could be huge. But let's just take that. With y as 1, x is approximately the square root of 4,000. And if you look at putting that value in when we come down here, when we're doing our test, we put in the value here of 20 for our minimum, then that's going to give you, into our formula, see where you find y there, and we've got our x. That's going to give you a much bigger value for the surface area. It's actually going to be a very big surface area, because it's going to be a big flat box with very little depth there. Y is going to be very small. So can you see that for large x, and you really should make this comment here about the end conditions. Here, when we will just slide back up here again, I think here where we make x is greater than 0, or x could tend to infinite values, this will make the surface area very large, because it's going to be a very big flat surface with not much depth. So that should be mentioned there. So anyway, going back to this, we've got 20. We can have very large x going out here. So subbing in 10 and 30, we find it's negative and then a positive. So that is a minimum, or second derivative, subbing in x is a positive in here, we'll always give a positive. So that checks that it is a local minimum. And then you've got your 20 from the turning point there, and then subbing it in for y, I've got 10. So this is a shape that gives the minimum surface area. And the maximum surface area would be when you flatten it all out and have all this large surface area here with y tending to 0 and x actually, well, it could be 40,000, but it could theoretically be infinitely small height there. So just thinking around those problems. Okay, so let's go on, and here's some for you. So here's the first few here, 1 to 4. I think I've split this into several different sections. There's 30 problems. Give you the first 19 of the same sort of type, then talk about another type. So pausing that and having a go. The answers to the first 19 are at the end of the set of 19. So let's have a look. That was up to 4. And then let's go to 5, 6 and 7. And then the rest of 7 there. Eight and 9. I'll just go back up a bit there. 8 and 9. 10 and 11. 12. they're all interesting problems. I don't think you're going to have time to do all of them. 13 and 14. 15 and 16. Let's come back here. 17. Oh, let's go a little bit further here. Let's go to 16, 17, 18, 19, I think. Okay. So what we'll do, just take note here of a little hint. If you have a square root in your formula, sometimes it's to say, well, okay, if it's a positive, then the maximum for the function is going to occur when the square of the function is a maximum. So square both sides, and dA by, instead of dA by dx, because it's got a root in it maybe, do dAx squared by dx, and put that equal to 0, if this thing's got a square root in it. Okay, so let's come down now and have a look at the solutions. 1 to 3. You come down to 4, a fairly long one, 4. 5. What have we got there? 5 and 6. 7 and 8. 9 and 10. 11 and 12. 13 and 14. 15 and 16. 17 and 18. And then number 19. Okay, so there's 11 more to do, so stay with me now and let's go on. Let's do another example. This one here is a drain, a practical problem here. We've got a animal enclosure, right angle triangle with one leg being a drain, so one side there, and we've got 300 metres of fencing. Here we are. This is a little bit more of a stage problem. So show that AC is that, if AB is X, so start to write that on the diagram here. This is X, and AC squared. How much fencing has he got? Well, he's got a total of 300 metres. So if he uses X there, this will be 300 take X. This doesn't need fencing, that's a drain. So by Pythagoras, putting it down in full form, because it's a show that up here, dangerous. They're giving you the answer. You must be very particular in showing all the steps of how you got that. With a diagram is important, remembering the 300 metres from up above. Okay, so then they want you to find the maximum area of the triangular enclosure. And so here we're going to use that squared idea. So the area of the triangle, let's just go back up here, is a half base times height. So it's a half AC by X, and we've got this ugly square root in here. So rather than work through with the derivative of that, because this is going to be a positive, when we square it, we're going to get this, and the maximum value of that, A of X, is going to be when that occurs, it's going to be when the maximum for the square occurs. And so you can just square it and put equal to 0, sign diagram. So it looks like X is 100, is going to give us our maximum. So we say that, and therefore we then go back and substitute 100 back into the A. Sometimes the problem asks you for when, like what length is required, like the cake tin, and they don't actually ask you for the volume. Other times they'll ask you for the dimensions and the area, the actual value of the function. So look carefully at how much is required, and then there's our diagram at the end of what it looks like. Not always required here, but just checking that through. Again, you might look at this one in terms of n conditions. Obviously, x can't be less than naught. What's the biggest x you could have? Well, I guess it's really like this, isn't it? So that x is huge, x is virtually the whole 300, and there's virtually no other length there. So is that right? Is that what we're going to have if x is like that? Yeah, so the drain, so let's have a look. So let's go back and let's maybe just draw this differently. We've got our drain. Now what can we do? We could have x is very small, means we'll go further out to the drain, and x is very large as we come in. So either of those are going to give you a smaller area, but some sort of statement about the end conditions really should be made. All right, so let's have a look at these questions here now. We're going up to 30, so 20 and 21. So these are ones where it is going to pay to square the function before finding its derivative because it's got a square root in it. And then here 21, 22, 23, 24. Interesting little problems these. 25. Hang on, and we've got the solutions coming up here now. There's 25. And then under those now the solutions, 2021 to 23. Hang on, we'll go a bit further for these here. We haven't quite got them on the screen. 24, 25. And we've got one more little set, and that's to do with this thing here. Hayes are talking about sometimes technology doesn't provide easy solutions because we have given general things like the sheet of metal is just a sheet of metal, a square sheet of metal. We don't know how big it is, so you can't put it on the calculator because you've got A's in it. So it's A by A, and you're going to have to work in A land. What size square should be cut out when bent in an open box so you have maximum volume? So the volume is length by width by depth. A take 2x by A take 2x by x. Remember, same as before, cutting x out of here. What are you going to have left? A take 2x there. Alright, so we have it all in terms of a single variable, and then we can, well, you could square that out and multiply by x, or use the product rule, derivative of the first, second unchanged, plus first unchanged, derivative of the second, whatever. Don't forget function of function, derivative of this term in here. And again, go through, and it's in A land now because they have generalised it. It's just a square box. So derivative is naught when either of those factors are 0. And also noticing here that both of the lengths must be greater than naught. X must be greater than naught, and here A must be bigger than 2x. So x is between naught and A on 2. You can't cut bigger squares out than your and have a 0 for A take 2x. A take 2x can't be 0. Alright, so we have our end conditions, if you like, and just going back up here. So here A over 6 is the only value in our range there, so what we've got to do is work with that. We'll just come down here a little bit. Yeah, okay. So the other value, which is A on 2, is on the borderline. That's no good because A on 2 gives us a 0 length there. So here, when we get the second derivative, using a second derivative, because it's very hard to work with a value here, A on 6, and do a sign diagram for V dashed x. Very hard because you have to put in what? A on what? What's less than A on 6? A on 10, and A on 5 or something. hard to work with those to work out the signs here. So it's easier to get the second derivative, which is the product rule again, and go to there and then sub in a on 6. And because it's less than 0, we say it's a local maximum. So the answer is when the depth of the box is a on 6, or a sixth of the original length of the box. If you remember, we started off saying here that this was A and A. So therefore, when we build our box up here, this depth has to be A on 6 to give us the maximum volume. Alright, so that's an interesting question. There are a few like that coming up, so let's go down and have a go. So 26 and 27 don't have numbers in them, so this is what you need to build up for test and exam performance, working with variables. Okay, so there's 26 and 27, 28, 29 and 30. Alright, we'll have a go. And solutions coming up down the bottom now. I'll just go down there to 26, 27, 28 and 29. These are a bit more challenging, these ones. And 30. So have a go, and good luck with those. Some fairly challenging problems there. You won't have time to probably do all of them. Do some of each batch. And I hope you've enjoyed your calculus journey. We'll be coming back with another presentation later on further calculus. So at the moment, though, it's cheers from me. Keep working hard.